So next up is Green's theorem. Green's theorem is going to be another way to integrate vector fields over curves. But just like the conservative vector field theorem, this only works in very specific situations. So first, it'll only work if we have a two-dimensional vector field. So a vector field that only has two components. Two, it only can be used if we're working with a simple closed curve. So a simple closed curve is a curve that does not intersect itself. So here is a closed curve, okay? Starts and ends in the same spot. Here is a simple closed curve. And so the difference is that a simple closed curve bounds a single area, where just a closed curve can bound multiple areas, okay? And we need that because the way we're going to basically do this and integrate a vector field over a simple closed curve, and since it's closed it will be circulation, would be one way to describe this, is to integrate the vector field over the area that the curve bounds, okay? And so we're going to look at this area and integrate over there. Well, if you're integrating over an area, that involves double integrals, okay? We integrate over intervals, we have a single integral. Integrate over areas, we have a double integral. Integrate over volumes, we have a triple integral. So this will have to involve a double integral, okay? We're also going to work with the boundary orientation. So the orientation of this curve in the theorem is going to require this curve to be counterclockwise, okay? Counterclockwise orientation. But the curve will bound some domain, okay? So this is the domain that the curve bounds, okay? All the space inside the area inside. And since the curve will bound the domain, we can label the curve as this boundary of the domain using that symbol there, okay? So just remember some notation for some vector field integrals. You write it this way as one way to say we're integrating a vector field over a curve. If it has two components, we could also write it this way: the integral of f1 dx plus f2 dy over the curve. That's just another way to write it. So what Green's theorem says is let D be a domain whose boundary is a simple closed curve. Okay, the curve one bounds this domain, and it's also oriented counterclockwise. So then, if we wanted to integrate a vector field over that curve, and that vector field has two components to it, so it's a 2D vector field. To do that, we could simply compute this integral, where we integrate this function that comes from the vector field itself over the area that the curve bounds, and we're therefore doing a double integral. Now this would only make sense to do this if the vector field is not conservative, because if it is conservative, since this is a closed curve, we know the answer is going to be 0. So we wouldn't bother going through all this. Also, if it's conservative, these two things will equal each other. Those two partial derivatives will equal each other. So again, doesn't make sense to really even think about applying this to a conservative vector field. It's a little overdone for that. But what we will do is apply it to 2D vector fields who are being integrated over simple closed curves. And so all we do is we compute this function, we define the domain, and we go ahead and do a double integral. Now once you have a double integral, everything that you've done with double integrals will start applying. So all the stuff we learned about double integrals could apply to any one of these double integrals we get. You could convert to polar coordinates, you could split it up into two single integrals if you have the properties that hold that to be true. Any of those things will work. So here's an example. Compute the circulation. So it's already telling you you're going to be working with a closed curve. For this vector field, which happens to be a 2D vector field, around the triangular path C, where C goes from point 0, 0 to 2, 0 to 2, 2, then back to 0, 0 again. Well, if we look at that curve, 0, 0 to 2, 0, that's 2, 0, up to 2, 2, then back to 0, 0. That is a simple closed curve with a counterclockwise orientation. So the curve has everything we need. The vector field is 2D, so that has everything we need. So now we'll apply Green's theorem. Well, first thing we need to do is calculate the partial of f2 with respect to x minus the partial of f1 with respect to y. That'll be the function we have to integrate based off of the vector field. So f2 with respect to x is going to give me 2xy cubed minus f1 with respect to y. Well, there's no y's in f1, so that'll be 0. So we'll have 2xy cubed. Then we have to define this domain here in terms of x and y. Right? So let's look at it. Y goes this way. On the bottom end, it's hitting the x-axis, which is 0. On the top end, it's hitting this line every single time. So we need to figure out what this line is as a function, and that'll be what y is between. Well, that line goes from 0, 0 to 2, 2. I could easily say the line is y equals x. If you didn't see that right away, you could say, all right, well, I got to write the equation of the line that goes from this point to this point. How would I do it? I'd find the slope. So change in y over change in x. So that'll give me 1. Then I'll use this point as my point and use the point slope formula. I have y minus y1 equals m times x minus x1. So y minus 0 equals 1 times x minus 0. And you see that's where you get y equals x. So on the top end, y is hitting that function, y equals x. Next, what we want to do is see what x is between. So x clearly goes from 0 to 2. So there is your domain. And therefore, if we're going to integrate this vector field with respect to the curve, and it's a closed curve, we're simply going to do the double integral of this function with respect to y and x, where y goes from 0 to x and x goes from 0 to 2. And we integrate with respect to y first because y was between functions. So that's going to be 2xy to the 4th over 4 between 0 and x. So we plug x in, we simplify, we're going to get x to the 5th over 2. Then we integrate with respect to x. And so we're going to get x to the 6th over 12 between 0 and 2. So we're going to get 64 over 12, which is 16 over 3. So there you go. That allowed us to integrate the vector field over the curve without having to use the conservative vector field theorem, because we couldn't. This is not a conservative vector field. Or the original formula we had for integrating vector fields over a curve, because we would have to parametrize this curve in order to do that, and we didn't really want to have to do that. And so Green's theorem allowed us to get this done. So you now have 3 ways to integrate vector fields over curves. And you need to decide which one works best for a given problem. Here's another one. Now, in this one, it says to use Green's theorem. I mean, you're not always going to see that. But why are we going to use Green's theorem here? Well, one, we have a 2-dimensional vector field. Here's F1. Here is F2. Okay. That's the 2 components of our vector field. And the curve that we're integrating over is based off of the semicircle, y equals the square root of 4 minus x squared. That's the top half of a unit radius 2 circle. Okay. So negative 2 to 2, 2 up here. That's this y equals the square root of 4 minus x squared. And we want to go the line segment from negative 2, 2 to 2, 0. So if we're going from here to here, you see we have that counterclockwise orientation. And we have a simple closed curve, and that it's bounding this area in here. And we have everything we need for Green's theorem. That's why we're going to use Green's theorem for this. So we want to calculate the partial of f2 with respect to x minus the partial of f1 with respect to y. So f2 with respect to x, this is the only piece that had x's in it, so that's going to be 2xy, minus f1 with respect to y, this is the only piece that has y's in it, So it'll be a minus 2y. Double negative makes it a plus, so 2xy plus 2y. So that's what we're going to integrate. We would define this domain based off of y and x. So y goes this way. So on the bottom end, you're at the x-axis. And on the top end, you're hitting this curve. So that would be square root of 4 minus x squared. And x's range between -2 and 2, because we want to fill all of this space in. So we create this double integral where we're integrating 2xy plus 2y with respect to y and then x, where y goes from 0 to that square root of 4 minus x squared, and x goes from -2 to 2. Now, you may look at this and say, well, look at this area. This area, being circular in nature, might fit out better to look in terms of polar, right? R and theta. And if you want to do that, that's fine. This is a double integral. You would just have to convert your function to polar, your differential to polar, and then your limits of integration to r's and thetas instead of x's and y's. Totally doable. Go for it if you wanted to do that. In this case, I'm just going to do it in terms of x and y's for right now. So -2 to 2, still going to be there. We integrate with respect to y. We get xy squared plus y squared between 0 and the square root of 4 minus x squared dx. Okay, then I am going to plug in this in for y. Squaring the square root makes it really nice. So I'm going to do x times 4 minus x squared plus 4 minus x squared dx. I'm going to multiply all this out before I integrate. So I have -2 to 2. I'll have minus x cubed minus x squared plus 4x plus 4. That's what I'm going to integrate with respect to x. So once I integrate with respect to x, I have minus x to the 4th over 4 minus x to the 3rd over 3 plus 2x squared plus 4x. And that'll be between -2 and 2. So once I plug -2 and 2 into that and evaluate, just do the basic computation, I end up with 32 over 3 as the final answer. And again, done using Green's theorem because of what we had in front of us. This is not a conservative vector field in that these two partial derivatives don't equal each other, clearly. So conservative vector field method is out. I have to parameterize the curve that bounds this area in order to use the original method we talked about when we first started integrating vector fields. I really don't want to get into that for this problem. It wasn't necessary. But because we had a two-dimensional vector field and because we had a simple closed curve, Green's theorem was a great way to do this. And again, once you set up your double integral, if you go, I don't really want to integrate this function, this double integral in x and y in rectangular, I think it would be easier to be done in polar. Then go ahead, switch to polar. It's a double integral. Anything we learned for double integrals you can use to integrate this function. Once we switch it to a double integral, all the rules for double integrals apply.